Again, when it says three-phase Y to Y, that means you have a Y source and a Y load. So that's what that means. Y source attached to Y load. They don't have to be, you'll see soon enough, it doesn't have to be Y to Y. It doesn't have to be delta to delta. They don't have to match the source and the load. They could be different. Then when we have to do conversion there. So let's say we have a Y source, like this one. We'll call that A. This is N. This is B, minus to plus, and this is C. This is VAN. This is VBN. This is VCN. Now again, just a reminder about these connections. The magnitude, the only thing difference between VAN and VBN and VCN is what? The phase. So if VAN, for example, has a value of 120 angle 0, then VBN will be what? 120 angle what? Minus 120. And VCN will be what? 120 angle what? Negative, another 120 from this one, 240. So this is 120. Difference between this and that is 120. It's always 120. Why 120? Because they take 360 divided by 3, which is 120. So what you notice about these, that if you look at the magnitude of VAN, it's equal to the magnitude of VBN, which is equal to the magnitude of VCN. These numbers are, if it's balanced source and balanced load, these actually will be equal for balanced source. These angles will be 120 off. If it's not a balanced load, then everything is off. If it's a balanced load, if you take VAN, add to it VBN, add to it VCN, the result will be always 0. Let's prove that one, and I get to show you how this calculator works, the 86, in case you borrow it. So if I take this calculator, everything quit, here we go. Let's add them, parentheses, 120, angle 0.
The glare from the light.
Okay. Add to it, 120, angle negative 120. I forgot to check and see if I'm in degree mode or radian. We'll know quickly. 120 angle 240 or negative 240. By the way, instead of negative 240, sometimes they write what? What's equivalent to negative 240? Positive 120 equals 0. Now, color terminology you might see. It says a positive phase sequence. Notice we're in VAN, where is it? Equals some peak value with angle 0, then VBN is minus 120, and VCN is minus 240. It says this is known as positive phase sequence, or ABC phase sequence. So you'll hear that. You'll hear that every once in a while. And the problem would say we have a positive phase sequence source, or an ABC phase sequence source. That means VAN equals VP angle 0, the other one VP minus 120, and the other one VC minus 240. Now, where's 12? Now, what about if VBN is equals VP plus 120 and VCN VP plus 24 instead of negative? This is known as a negative phase sequence or a CBA phase sequence. So when you look at the problem, sometimes they can tell you it's an ABC phase sequence or a positive phase sequence. That means the angles will be negative. If it's a negative phase sequence, then the angles are positive. You add 120 for VBN and you add 240 to the other one. So make sure you're just aware of that. You'll hear that in the problem. You will see it. It will say a positive phase sequence, a negative phase sequence. So that'll let you know if it's positive angle or negative angle. And notice there's a nice picture of that. A positive or ABC phase sequence, that's picture A. VAN is VP angle 0. VBN is negative 120. And VCN is negative 240. It's like you going clockwise. If it's a negative or CBA phase sequence, VAN is 0. This one's plus 120. This one plus. You're going counterclockwise. You know. Now let's say we're going to attach this to this source. And by the way, if you know, and I think we did that last time, we calculated what VAB. If you know what VAN, immediately you know what this one and that one. You also know what VAB is. If you remember last time, we said if VAN equals some peak value, angle theta, then you can get VAB. VAB is going to be the square root of that 3 times that number. That's the magnitude of that. And the angle, what do?
30.
Add 30 degrees to it. So in this case, VAB will be what? What is the square root of 3 times 120? And the angle will be 30 degrees. And VBC is going to be the square root of 3, angle 120. And this angle is going to be 120 degrees subtracted from that. What is 30 minus 120? Is it negative 90? And VCA, not AC, VCA equals the square root of 3 times 120. Subtract another 120 from this, that will make it what? Negative 210 degrees. They call this voltage VAB, VBC, and VCA. These values, the magnitude of that is called the line voltage. So VL, that's the line voltage. It is equal to the square root of 3 times VP. Now let me take an example and show you how we use that. I'm going to give you a balanced source with a balanced load. So here is my source. 200 angle 0 RMS. That's VAN. .200 angle 0 RMS. This is VBN. This is VCN. Which will be 200 angle negative 240 RMS. This will be 200 angle negative 120 RMS. Now we're going to attach that to our load. And let me give the load some values here. What are the values for the load? I have a resistor and an inductor, a combination of that. It's a resistor and an inductor. But I don't have to know that. This is my load. I said, you know what? It's 100 angle 60. It's a balanced load. So this is capital C, this is capital N, this is capital B, this is capital A. I'm going to attach this assuming these wires are perfect, there's no resistance to them. That won't last long. We'll change it. A to A. I'm going to attach B to B. I'm going to attach C to C and N to N. And the question, what is the current from A to A? This current. What's the current from B to B? Notice I use lowercase for the source, capital case for the load. That's common notation. So I sub AA, this current is going to be coming down here, has only one way to go, through that. I sub BB comes through this one. So this I sub AA, again. This is I sub BB. This is going in I sub CC. Well, we got a node here. All these currents coming in. What's going to happen? There has to be something coming this way, right? I'll be interested to know what that current is. All the current entering the node should equal the current leaving that node. I got this going in, this going in, this going in. Now something got to come out. Or maybe. So what I'm going to do to solve this, since we love balance load with balance source, why?
It'll be zero, right?
Well, it could be.
Well, they're both the same voltage between those two nodes, two ends.
Correct. We'll see if it is. You might be right. I'm not saying you're not. Dave, you could be right. If this is actually a balance load and this balance source, it will be zero. But I want to prove it. Sometimes these are not balanced, then it changes things around. So now let's see what's going to happen. To find I sub AA, I only have to look at one branch. Let's take a closed loop, this one. That's a closed loop, see it? So let me draw that loop there. This is what I see. Can I find that current? What is I sub AA? Ohm's law. You know the voltage, you know the impedance. You divide them. 200 angle 0 divided by 100 angle 60. And you have what? 2 angle negative 60. Once I have that, I don't have to waste my time looking for I sub BB. I can do it the way I did this one. But if you look at I sub BB, the only thing difference is going to be this voltage minus 120. So if I put minus 120, 200 over 100, that's still a 2. And when you divide, you subtract. You got negative 120 minus 60, which is what? Negative 180. Or take that number and subtract from it another 120, which will make it minus 180. And I sub CC, it's also going to be 2, and subtract another 120 from this. Is that 300? Now, when I asked what's the current going through that, David said it's 0. Let's see if David is right. Let's do KCL at capital N. The current going in, which is I sub AA, plus I sub BB, plus I sub CC, should equal the current leaving. I label that I sub capital N small n. 2 angle negative 60, plus 2 angle negative 180, plus 2 angle negative 300, equals I sub n. Does that equal to 0? Let's see. There's my calculator. 2 angle negative 60. I forgot to turn it on. 2 angle negative 60 plus 2 angle negative 180 plus 2 angle negative 300. 0. So the math seems to agree there, that the current going in, that's the neutral node, is 0. So by doing one branch there, we got actually all the stuff we need to know. We know what this voltage here, I know this voltage here, I know what this current, I know what this current, all the stuff. Okay, let's try another one. Another example. We have time? Yep, good. Here's the problem. Let me write the problem down. A balanced three-phase system with the line, with a line voltage. Gotta be careful with the word line. With a line voltage, let me underline the word line. Voltage of 300 volts is supplying. Let's bring in the power here. A balanced Y-connected load, a balanced Y-connected load with 1200 watts. The word watts, again, important to us because that tells what average power. At a leading power factor of 0.8. Leading, that means theta is negative. Power factor equals 0.8. The question is, find the line current and the per phase load impedance. Per phase. Let me look at my load. After you finish writing, we'll look at the load. It's a Y balanced. So we have a load that looks like this. This is capital A, capital B, capital C, capital N, capital because it's a load. Y connected load. It says the load, the source supplied 1200 watts to the load. 1200 watts to these three. Since it's a balanced one, each one of them is 400 watts. That's what that means. Each one of them has a power factor 0.8 leading. .8 leading. That's the power factor. The only thing that bothers me in this problem is says the line voltage. Well, maybe 5 minutes ago, I derived something and I said the line voltage, it is equal to the square root of 3 times the phase voltage. So if this was actually connected to a source here, I'll do a source here. Well, A usually goes to A, so let me just redraw that Y to Y, a little bit nicer.
Could you just make that one A? The other one
Yeah, then I like them that. I know I could.
do a mirror image of it?
Yeah. But what they're telling you is actually this voltage from A to B, this is B here, the magnitude of that is 300. So to get VAN, or the magnitude of VAN, it's going to be VL divided by the square root of 3. So it's going to be 300 divided by the square root of 3, and that will give me what? Divided by the square root of 3. 173.2 volts RMS. Okay. Now, looking at that picture, we know what the voltage here is. We know what the average power. We know what the power factor. Can we figure what the current through it? If you remember, average power, P average, equals VRMS, IRMS, cosine theta V minus theta I, right? And what is theta V minus theta I? We call that? That's power factor, right? So I know that's 400. I know the voltage is what? 173.2. I know the current. Well, I don't know the current. I'm looking for it. That's I sub A to N. That's the current going down here. Times the power factor, which is 0.8. So the magnitude of that, I sub AN, is going to be 400 divided by 0.8 divided by 173.2. 2.88. Or 89 amps. Now I don't know what actually, I have no idea what the angle for VAN is. It's 173, the magnitude. So the Z per phase is going to be the voltage per phase divided by the current per phase. Well, the voltage per phase is what? 173.2 some angle theta, called theta V. The current is going to be what? 2.89 some angle what? Theta I. So you divide the coefficient, which is what? 173.2 divided by 2.89. It's 59.9. The angle will be theta V minus theta I. Oh, wait a minute. Wait a minute, wait a minute. That looks familiar. Theta V minus theta I. What's the definition of power factor? In this case was 0.8. Isn't that cosine theta V minus theta I? So if I want just theta V minus theta I, what do you do? Inverse cosine of 0.8 is theta V minus theta I. And I go to my calculator, second cosine 0.8, roughly 37 degrees.
It just made me do a lot of the numbers we have lately as far as angles go when we do the
Theta V?
theta V ends up with like around 37 degrees.
Well, that's because we are doing a lot of power factor 0.8.
Is that like, is that just because it's a normal power phase, or is it just
Usually between 7 and 9, 0.7, you know. So now that current here, here's the thing. Is it leading or lagging? What was the power factor? Leading or lagging? Because remember, the cosine could be positive or negative here, right?
it's leading?
So it's leading, that means what? Is it positive or negative? The angle has to be a negative 37 degrees. So the impedance per phase is actually that number. I think that's what the question. What is the per phase load impedance? It's this number. 59.9 or 60 if you want, negative 37 degrees. Maybe I can do one more. Okay. Here actually we have two Y loads. Let me show you the picture per phase, because otherwise it gets really ugly. Well, before I show you the per phase, just heads up. This is what we have. We have a source, and I'll go to per, okay. I won't connect everything, because if I do connect them, I'm in trouble. And I have two loads here. And the two loads are connected in parallel. This has like this, and the B is the same thing. The B is connected A, small n, small c, capital C, capital C, capital N, capital N. You have something like this. And you can see why I don't want to draw this like or the whole thing. But we have two Y-connected loads in parallel attached to a Y source. So if I look at just per phase, this is what I'm seeing per phase. I have numbers for these, I just didn't write them down.
So those are both capital A's.
Yep, because they're both loads. And the numbers I have is all I know, this one absorbs 200 watts. So this, we don't know what R is. But this one absorbs 200 watts. The other one, it's the same example we did before, 400 watts. Power factor 0.8, and it's leading. That means a resistor and a capacitor. That's what that means, leading. And the question now, what is this current, the line current from A to A? Assuming this voltage here, the same we did before, the 173, the same example as before. What was it, 173.2? When we did the math?
It was 173.2.
173.2, some angle theta V. You know? Well, we knew what the current here. Or we calculated with the Z impedance here. We did that. Since I have the answer from the first one, it's up to me what I do now. Whatever I want to do, I can work with it. If you remember, we calculated Z impedance for that one. That's if I cut this one, that's the previous example. I can take the Z impedance in parallel with this, the product over the sum, find the new value, calculate that current. Or I can find the current through each one. We know what the current through this. We calculate that current through that. What was the current through this one? From before, what is that current? 2.89. The magnitude, some angle here. Well, this is pure resistor, so this has an angle of 0. The current for that, the 200 watts, equal the voltage is 173.2 times the current, which is I2 here. And since that's pure resistive, there is no phase shift. Power factor is 1. So I know what I sub 2 is.
What's the one?
That's the power factor. That's
How did you get the power factor?
pure resistor.
Oh, right. Okay, I know it.
200 divided by 173.2 equals 1.15. Angle 0.
You got that by dividing 200
Yep.
200 by 173.2.
Mm-hmm. Because my power factor is 0.8, that tells me the difference between this voltage and that voltage has to be 37 degrees, and it's leading, that's negative. So that's I sub 2. I sub 1 is going to be 2.89 angle negative, or the inverse cosine, that's how you figure what that angle is, of 0.8, which happens to be 2.89 negative 37 degrees. Negative because it's leading power factor.
Leading is negative, lagging
Is positive, yep.
is
So-
by the ice.
Yep. Can I do I sub AA now? It's I sub 1 plus I sub 2. And we know what that current. That was what the question. What is the current? That's 3 point, do the math, 87 angle 26.6 degrees.
I'm about to do it out on my calculator. .87. Yeah, that's what I got. I got 26.7.
Yep.
I'm assuming it just rounded out.
Yep. So that's what the current for that circuit.
So like when you like get the power factor, like it gets the difference between the two angles.
Yes.
voltage, but is there a reason why we were able to say that the difference between the two voltages was negative?
'Cause it's
Well,
leading.
I2,
Leading.
I1.
The word leading, it says negative, lagging, it says positive voltage. That means theta V minus theta I is here. Theta V, because leading, minus theta I. It's a leading power factor. This has to be a negative value if it's leading.
So did we just assign that theta V was 0?
There could be any number. Doesn't really matter. The difference between them is going to be that number. So if it's 0, that's the value there. Because the reason I said doesn't matter, because I'm using that angle also for this. So if it has an angle, that angle is going to show up here. So it really becomes no factor what that angle is. So to make my math easy, I make it a 0, yes. And if it's negative for, I said it backward here, for lagging power factor here. Oh no, I was right. I wrote leading here, that was correct. And theta V minus theta I, when it says lagging power factor, that's positive. Lagging power factor. So if this is leading, the difference between them is negative. If this is lagging, the angle between them is positive.